All right. Hello, everyone. Thanks for joining us for this seminar with Eric Moss on predictive engineering and artificial intelligence. I'm Brianne Tenga, and I'm the Hawaii section chair. We're excited to welcome Eric back. If you're not aware, this is actually the third predictive engineering seminar that we've had with him, with the previous two being over the past 2 years. But just a little bit about Eric. He's a retired senior director and technical fellow from Medtronic. Now he works with the Ad Astra Foundation. I guess I'll give it to you, Eric, if you want to do a little intro of what Ad Astra is, and then we can go
Okay,
into it.
my gosh. Yeah, so Ad Astra helps basically young professionals, young, mostly STEM people, science, technology, engineering, math people, to make it through those early years in the transition from, the university education and into their life after school. And so helping people with the transitions for some people, a lot of challenges involved. So that's where Ad Astra kind of has been focused, including people who are immigrants from other countries and are in engineering curriculums, for example, in the United States, and young women, men, minorities, and everything else. So helping them get a little bit of extra help in those early years of their professional career. All right, and I guess should I go ahead and get started, I guess. Well,
Yeah, go for it.
okay, welcome. So yes, predictive engineering and artificial intelligence. A topic I was asked to talk about, as Brianne mentioned, my last two talks have been about predictive engineering, and asked this time to go into a little bit about artificial intelligence. And you saw on the introduction a little bit of controversy in here, perhaps, probably not perhaps, probably actually. And I try to align it with what I sometimes incorporate into like design for Six Sigma, critical thinking. And some of you have heard the word critical thinking, but critical thinking involves challenging assumptions and the way people think and make decisions and things like that. And so critical thinking by its very nature can often be provocative. So that's my intention talking about artificial intelligence today, as being somewhat provocative. And in the course of doing that, it will often not be politically correct. So if I offend anybody in the course of today, I apologize in advance. My apologies, but I will go forward anyway and challenge some assumptions and some thinking and things not like that. And if I end up being not politically correct, and I probably will not be politically correct all the time, again, I've apologized. With that apology in advance, so three main things I want to go through in the course of today. I'll talk about, since we're talking about predictive engineering and artificial intelligence, what do they have in common? And I'll hopefully cover that pretty well. Then can predictive engineering, where most of my expertise may lie, help us better understand and leverage artificial intelligence, that I'm abbreviating AI. And then lastly, and a little bit of a more optimistic, hopeful thing, can predictive engineering perhaps even help improve some of the issues that I'll talk about with AI? And so that's kind of our topics. Let's start at the top. What do predictive engineering and artificial intelligence have in common? And I'm going to start off by talking about predictive engineering and intelligence rather than artificial intelligence. So predictive engineering basically provides tools and statistical methods, conceptual modeling tools like P-diagrams that you may have seen in my earlier two sessions if you happen to watch them, and statistical methods like design of experiments, regression analysis, response surface modeling, that'll give us ways to learn by analyzing data and to deal with challenges, new and difficult situations, improving existing processes, developing new processes and new products. Intelligence, according to the Merriam-Webster dictionary, the ability to learn or understand or deal with new or trying situations. Hopefully you start to see the analogy already. Or another definition, the ability to apply knowledge to manipulate one's environment or to think abstractly, and they put in this concept as measured by objective criteria, such as tests. And so, yes, if you look at those, there's a pretty clean similarity, analogy between what we're talking about with predictive engineering learning and intelligence learning and applying knowledge and analyzing data and so forth. And we'll see more of this as we go on, but I started with intelligence. So showing you a little bit of that linkage there. All right. So in terms of where I want to go with this early on, there's this book, actually I have a copy right here on my desk, so it's show you, bestseller by Daniel Kahneman, the winner of the Nobel Prize in Economics in 2002, who I've mentioned in my earlier two talks. And his book, Thinking Fast and Slow, talks about two types of thinking. Those of us on this call who have science, technology, engineering, math background, probably almost all of us have engineering backgrounds, we may notice a difference between the way we approach problems and challenges and make decisions compared to our non-STEM friends and relatives. And that somewhat can be understood in the context of thinking fast and slow. Thinking fast is the way almost everybody makes most decisions in their lives and approach most of the challenges in their life. Thinking fast. The formal name for it is heuristic thinking, and there's a book about that, or several books about that. Heuristic thinking. So heuristic thinking is we make decisions based on rules of thumb, like if the price is too low, there's got to be a catch. Or if I don't know what to do, I'll either follow what other people are doing or do what the experts tell me to do. And we're going to build on that in a moment. I'll get to thinking slow on this slide in a moment, but let's talk about heuristic thinking. The analogy in my mind in the world of artificial intelligence and machine learning is what we would talk about as correlation and classification. And I'll try to show you that linkage on the coming slides. So in the world of artificial intelligence, building on statistical thinking that artificial intelligence builds upon, correlation and classification, they kind of go with heuristic thinking. Now, thinking slow is what we learned as engineers, model-based thinking, abstractions of reality, dealing with challenges, dealing with getting insights by dealing with models. Sometimes they are conceptual models, like P diagrams that I mentioned earlier. Sometimes they're physical models, like a scaled model of a bridge, mathematical models like Ohm's law, or that the power dissipation across a resistor is the voltage across it squared over the resistance value. Sometimes it's simulation programs like circuit simulation tools. But that's what we leverage in engineering many times, model-based thinking, using models, abstractions of reality. That doesn't go so much with correlation and classification. That goes with something that has a contrast. We say correlation is not the same as causation. Model-based thinking gets more to the world of causation. So I'm going to come back to this concept of correlation versus causation over the course of our talk today, but I'm going to start with correlation and classification, that left-hand side heuristic thinking. So in terms of probably in statistics, primarily statistics, we look at correlation in terms of a parameter called the correlation coefficient, the Pearson correlation coefficient, developed by Carl Pearson, one of the founders of statistics. That's used for continuous variables. There's an analogous correlation coefficient called the Spearman correlation when either or both of your input and output parameters are discrete. And the mathematical calculations for Pearson correlation and Spearman correlation are similar. So I'm going to group together correlation and classification because mathematically you deal with them with very similar parameters, the correlation coefficients. And as I mentioned before, the popular book, Thinking Fast and Slow, there is a book for people who make this their field of study called Heuristics and Biases, the Psychology of Intuitive Judgment, and edited by several people, including the same man, Daniel Kahneman, winner of the Nobel Prize in 2002, because he overturned the theory, rational choice theory, about how we make decisions in our lives. So taking this a step further and getting ready to be controversial. So I'm going to look at this correlation and how that leads to a heuristic, because I said I was going to make that connection between the statistical concept of correlation and the thinking fast concept of thinking fast and slow from Daniel Kahneman in that world of psychology. So imagine I went out there somewhere early in life and I bought something cheap, and when I did it, it broke down. Something went wrong. That correlation might lead to the heuristic in my mind that if the price is so low, there's got to be something wrong with it. There's got to be a catch. Similarly, all of us have had experience in our life where we didn't know what to do. Let's say I followed everyone else and things went well. So that correlation led to a heuristic, a way for me to make decisions. If I don't know what to do, I will follow the group, and that will be a relatively benign decision. Similarly, I had a situation where I didn't know what to do. I found an expert. I took the expert's advice. Things went well. That correlation, X and Y. So that led to a heuristic. If I don't know what to do, I'll do what the expert tells me to do. Okay. Correlation, classification leading to a heuristic. But that can go wrong, and I'm going to go with the wrong one. Let's say people of a certain race or religion did something really bad. And as a consequence, my heuristic is I now have a negative belief about that race or religion. So cognitive biases, so they call them heuristics and biases, there's biases or cognitive biases, can include racial biases, and religious biases. So that's the negative side. So I'm going to come back to that in a moment. So before I get into that, starting off with a controversial thing, let me be non-controversial for a moment. So this is illustrating an effort done by some image recognition, artificial intelligence, machine learning software many years ago, where they trained it with lots of pictures of plants and animals and people and objects. And then once they had done that training of this artificial intelligence for image recognition, they gave it a picture like this of a golden retriever in the snow. Looks like a cute golden retriever. And the artificial intelligence program immediately identified it as a polar bear. Heuristic. Hey, if it's got four limbs and it's kind of light in color and it's around snow, gotta be a polar bear. That is what heuristic thinking. So when we reproduce that way of thinking, thinking fast, heuristic thinking in the world of artificial intelligence, we get that kind of an error. But let me make it more nasty. So I'm going to go to the nasty part. So here's an article from the journal Racism and Technology. Racist technology in action. Image recognition is still not capable of differentiating gorillas from black people. So same kind of thing. They programmed it with all sorts of things. And when they showed it, photographs of black people, oh my gosh. So it was back in 2015 that the controversy first arose when Google released image recognition software that kept mislabeling black people as gorillas. And here it is from The Guardian in 2018. After Google was criticized in 2015 for an image recognition algorithm that auto-tagged pictures of black people as gorillas, the company promised immediate action to prevent any repetition of the error. That action was simply to prevent Google Photos from ever labeling any image as a gorilla, chimpanzee, or monkey, even pictures of gorillas, chimpanzees, or monkeys themselves. And here it is another thing. So Google fixed its racist algorithm by removing gorillas from its image labeling tech. So when you use artificial intelligence based on heuristics, you can also get artificial racism. And that's what we got here. So here's from 2018, nearly 3 years after the company was called out. It still hasn't gone beyond a quick workaround. So that's what you get when you get correlation and classification in your artificial intelligence. And then they try to update it. So this is all of last year. Google apologizes for missing the mark after the Gemini generated racially diverse Nazi. So somebody asked them to come up with illustration of 1943 German soldiers. Well, this is probably not exactly the way racially diverse soldiers looked in the Nazi regime. Then they also asked it for generate a picture of a U.S. senator from the 1800s. I don't think we had senators in the 1800s that looked like this. So that's what happens with correlation and classification and trying to auto correct for it. Not so good. Correlation and classification. So showing you a bit about what goes wrong when you rely on correlation and classification. That is the artificial intelligence analogy of heuristic thinking. So the problem here is artificial intelligence can mislead its users. And one of those is what I just mentioned, reliance on correlation and categorization. The analogy of heuristic thinking in humans can lead to racism and prejudice, racism, artificial prejudice. But let me go onwards from there. But before I do, show you a little picture of the world of artificial intelligence from my perspective. This is a Venn diagram. I modified a Venn diagram that I found on the web that looks almost the same as this. The one problem they had with the picture on the web is they had neural networks and Bayesian belief networks totally separated. And as I'll talk about later today, there's actually an intersection set. So I made my own version of it where there's an intersection set right there. But basically, a lot of the artificial intelligence out there is either rule and behavior-based systems or neural networks that rely on what are we even talking about, correlation and classification, and something we'll get to in a little while, Bayesian belief networks, and then the intersection of them with neural networks, Bayesian neural networks. But let's start on the left-hand side, and I start first with rule and behavior-based system. So rule and behavior-based systems have a very close tie-in to some of the statistical methods that we use in statistics in general and use in predictive engineering specifically. The tools like linear regression and logistic regression. You see a little Venn diagram I found on the web with linear and logistic regression and principal component analysis, some of the statistical methods that we use, and they're applied within this form of artificial intelligence, rule and behavior-based systems. Also, then, Another part of machine learning is decision trees. Now, the first time I got involved with artificial intelligence decision trees was in the 1980s. I was asked to help Motorola engineers in Chicago after we taught them classes on statistics. We threw so many statistical methods that they got confused. And so they brought in some experts in this early time of artificial intelligence in the 1980s to help figure out how do they make decision, what statistical tool to use in what situation. I gave them a decision tree and they found that useful. But here's a decision tree in an actual application. So one of the major applications that some of you are familiar with is when you go on the web, you go on Amazon or eBay or whatever kind of sites, they're starting to collect information about you to start to make decisions to figure out how to sell you something that you will buy. That's kind of how companies make money on the web, is basically gathering all that information and analyzing it and figuring out your buying behavior and figuring out how to sell to you something you will buy. Well, I had my own um, incursion into this field a few years ago when somebody asked me to help them, and I'm going to just show this to you. So this happens has a tie into a TV show many of us has watched, Shark Tank. On one episode of Shark Tank, and you see over there Mark Cuban on the left, he decided to invest in a little startup company shown over here called Eternova. And so I got involved in helping somebody at Eternova analyze a whole bunch of data they've been collecting about what led to sales of their product and service. And so we analyze it using a artificial intelligence machine learning kind of algorithm on that has now been incorporated in Minitab. It's called CART, registered trademark. And so we analyze it, and you see a little decision tree being generated, seeing how people make decisions if they are going to purchase, and using that then at the company to basically improve the chances of getting new clients, new customers. So that's a quick example. But going on from there, things that are wrong with artificial intelligence when you rely on correlation or heuristics, correlation classification. So besides the reliance on correlation, categorization, heuristic thinking leading to artificial prejudice, artificial racism, it can mislead in terms of causality. And I'm going to show you 6 ways very quickly here that correlation can lead in terms of causality. And some of them will be somewhat controversial, some perhaps less so, but nonetheless. So the first one was, we assume a factor X, an input X affects Y, but X is not the input, X is the output, Y is the input. So Y leads to X. I'm using the error of causality. So Y causes X, probabilistically causes X, when we assume X causes or probably causes Y. Let me give you a really interesting example of that, somewhat controversial, from the film from Al Gore, An Inconvenient Truth, about 20 years ago. So in his film, up on the big screen, he showed a graph over the centuries, over the millennia, of carbon dioxide content in the Earth's atmosphere, as determined by samples of ice, and the temperature of the Earth at that time. And you look at these graphs, carbon dioxide is in red, temperature is in white or blue, whatever you want to call that color. And as he shows this video, shows this image, Al Gore says, now one thing that jumps out at you is, do these curves ever fit together? Correlation. And they do, they're correlated. And the implication is, so higher CO2 causes higher temperature. But in fact, in these articles from MIT and from Science Bits or whatever else, in fact, if you look at the data, the carbon dioxide lags behind the temperature of the Earth by several hundred years to 1,000 years, typically average, I think, 600-year lag. The temperature changes first, and then the carbon dioxide changes. And what's really happening here, what they can determine is the effect is true, but it's the opposite direction of causality. So think, for example, of a closed bottle of Coca-Cola. It's got carbonated water, oxygen, or excuse me, carbon dioxide dissolved in water. Carbonated water, carbon dioxide dissolved in water. If you leave it out for a while and it heats up, it becomes stale because the carbon dioxide comes out of solution into the air. And that's what was happening. Just like the Earth, most of the CO2 is dissolved in our large oceans. It took a few hundred years when the temperature of the Earth rose, the carbon dioxide came out of solution and went into the atmosphere, and the carbon dioxide in the atmosphere content went up. So interesting things of that. So interesting. So the direction of causality, correlation may be real, but you may have the direction of causality wrong. Second example, we assume X causes Y because they're correlated, but really X and Y are both caused by a third variable, Z. I'm going to use a made up example, although other people use a similar example. So if you look at the temperature on different days and you keep track of ice cream sales and the number of people getting sunburns, you can make a graph of the number of sunburns versus ice cream sales, and you'll get a pretty good correlation. So a conclusion that artificial intelligence relying on correlation would come up with, hey, it's high correlation. Heuristic conclusion. If you don't want to get sunburned, don't buy ice cream. But in fact, both of them are caused by the temperature. On hotter days, more people buy ice cream. On hotter, sunnier days, more people get sunburns. And, this is actually an example from a website, What is Causal Machine Learning? A Gentle Guide to Causal Inference by Kenneth Stippa, showing the temperature causes people to buy ice cream, and it causes people to get sunburns. And so if you look at them, they kind of go up together, but it's actually a correlation caused by mutual causation. Next example, interaction. An interaction where the slope of y versus x depends on another factor, z. So I'm pulling up a real example here from a published paper. I have a link at the top of the page, and you have the PDF files on this if you want to look it up. So they're looking at for supply chain. Supply chain is very much in the news. I'm very much involved in supply chains as well. My PhD dissertation was on supply chains, and looking at effects of ways to improve your supply chain based on things like just in time versus not just in time, but looking at domestic versus international suppliers. And you notice that the slopes change whether it's an international or domestic supplier versus just in time, not just in time. So if you pull the raw data into AI to analyze the effect of just in time for suppliers, would you draw the wrong conclusions? Could be very, very confusing when there's an interaction like this. Let me go on to the next one. Simpson's paradox. Now, this one is one that a lot of people involved in artificial intelligence seem to talk about. In fact, a professor who is a fellow of the what do they call that society? Anyway, the Society of Artificial Engineers, named upon one of the people that are founded artificial engineers, Norman Fenton is his name, has given several talks that I've watched about Simpson's paradox and how it can screw up artificial intelligence. So let me mention what Simpson's paradox is. Here it is mathematically. Simpson's paradox occurs when groups of data show one trend, but it's reversed when you combine those groups. So let me give you a silly example of that, but imagine for a moment, someone here, you and a friend, are competing to play a game of solitaire or tic-tac-toe, and you're seeing who wins over the weekend. So on Saturday, you play 99 games and win 98 out of 99. So as a percentage, you won about 99%. Your friend on Saturday was kind of busy, only played one game, but he won that game. So on Saturday, he beat you because he got a higher percentage of winning than you did. Slightly better, but still better. On Sunday, you only played one game because you were busy, but you lost it. He played 99 games, only won one, but he won 1%. Well, 1% is higher than zero. So in terms of a percentage, your friend beat you on Saturday, your friend beat you on Sunday, but when you combine them together, you overall won 98 out of 100, 98% of the time. He only won 2 out of 100, 2% of the time. So overall for the weekend, you won, but he won on Saturday and he won on Sunday. Here, this is done as a correlation. This is actually a classification. This is a correlation example. Over here, I'll start with this simpler one over here. So you have y versus x, where another factor is blue or red. So when y versus x, for the blue, positive slope. Y versus x, for the red slope, positive slope. When you combine them together, a negative slope. And similarly, out of Germany, positive slopes, each individually grouping. When you group them all together, a negative slope. Let me show you a real life example of Simpson's paradox in action. So there was a study done many years ago about treatments for kidney stones. And they gathered the data in this published article, comparison of treatment of kidney stones, renal calculate. And so they had a treatment, open surgery, and another treatment that was non-open surgery, non-surgical, percutaneous nephrolithotomy, if I pronounce that correctly. So they looked at small stones, and for small stones, open surgery did better, 93% versus 83%. For large stones, open surgery also did better, 73% success rate versus 69. But when you combine them together, looks like percutaneous nephrolithotomy does better. How can that be? Well, it turns out they're leaving out the factor that the surgeon's making a decision. So for small stones, they more commonly would use percutaneous nephrolithotomy, but for large stones, it seemed more reasonable to do open surgery. And that bias, that combination, made that percutaneous lithotomy look better. And so you can get around this problem if switching from correlation based modeling to a causal model. So here's a causal model actually in a Gina.ai, a Bayesian model we'll mention later on, where they brought in the confounding factor being the decision of the physician based on the severity of the case, large stones versus small stones. And that basically explains this issue, Simpson's paradox. But if you're using just correlation, you might draw the wrong conclusion. Whether you look at things individually or you group them together, you will get different conclusions of what treatment to use. All right, going on from there. Another problem with correlation and classification. Too little data. Remember, just 2 points make a line. So my example here is, hey, if you wear a turtleneck, you can become a successful entrepreneur. A little tongue in cheek there, but it brings up a story that some of you may be familiar with. So this is from an article many years ago. Don't know why my red line's showing up over there. But anyway, um, uh, why Elizabeth Holmes reinvented her style. So Steve Jobs famously wore a black turtleneck to all the meetings. So a new entrepreneur, founder of Theranos, wore a black turtleneck. And the conclusion of the potential investors, Elizabeth Holmes is a female Steve Jobs, and her entrepreneurship and Theranos will be similarly successful. Yay! And, that too, all sorts of things. I think there's been a TV movie about this whole thing. Anyway, let me go on from there in a moment. So some of you may know that, and I may have mentioned this in my earlier 2 talks, that I've written a couple of books. And when you go out there, and I do recommend writing books, of course you come in your mind, well, how do I write something that really takes off, a real blockbuster, a really big bestseller? And because most people make their decisions based on heuristics, rules of thumb, and most people want to be successful, what you would want to do to have a really bestseller is write a book giving people heuristics for how to become incredibly successful. And one way to do that is, since it's based on heuristics, interview a bunch of people that everybody considers to be successful, see if you can find anything in common. Well, somebody beat me to it. This is from Fortune magazine. Gillian Joe Segal. I interviewed the most successful people alive. Here's what I learned. And there she is being shown with Michael Bloomberg with her book, Getting There. For my new book, Getting There, a book of mentors, I spent 5 years interviewing some of the most successful people alive. She lists them out there over there. Here are the 7 things they all have in common. And I don't know, maybe this book is fantastic. So if you want to be successful, buy this book. Look at those 7 things. Probably one of them is wake up early. So if you become an early bird, wake up early, you too can become a billionaire. But, I simplify, but, there probably are some good things in there, but it's based on heuristic thinking that, hey, if you find things in common, correlation basically leads to causality. If you do what they do, you will be similarly successful. Okay, staying on this topic of too little data for one more moment. 2 points make a line. If artificial intelligence, machine learning relies on big data, lots and lots of data, if the artificial intelligence learns from the data, not based on any prior model, the question is, can artificial intelligence work in situations where there is very little data for your data mining? For example, artificial intelligence for supply chains for low volume products might fail in that situation because there's not enough data. Artificial intelligence for treating rare diseases. And I take this a little bit personally because I happen to have a rare disease. I was a Mayo Clinic example because there's 5 of us in the United States that have my rare disease. Not going to find anything through artificial intelligence for my disease. Very unusual situation. All right. Then what about the other extreme? Instead of too little data, what about too much data? If you throw enough big data, enough data, and machine learning, artificial intelligence, you may come up with something called spurious correlation. And there's a website that's dedicated to it. Here's the website at the top. You may read it. And they have lots of funny examples. But if you have enough data, you can find correlations even when they are complete and total nonsense. So there's a high correlation coefficient of 0.9926 between the divorce rate in the state of Maine and per capita consumption of margarine. So if you don't want to get divorced, I'm not sure which direction, I guess, eat less margarine if you don't want to get divorced. Here's another one. Worldwide non-commercial space launches correlates very highly with sociology doctorates awarded in the United States. So if you want to have more non-commercial space launches, award more sociology doctorates. So you get nonsense correlations. They call them spurious correlations. And there's a whole website full of examples of these that when you look at big data. So summarizing, artificial intelligence can mislead users. First off, that reliance on correlation and categorization, heuristic thinking, can go to the negative side of that, that they cause basically biases. And those biases can include racial biases, prejudice in general. And as I said, correlation can mislead in terms of causality. And I showed, 6 ways that can do that. All right. So that's talking largely about that. I want to go a little bit into neural networks. That gets a lot of press lately. Yeah, good. Yes. Um, so yeah, good little comment from me, and I'll get back to that at the end of this. So let's talk a little bit about the other one that's kind of correlation and classification based neural networks. Now, neural networks are kind of interesting. They're based on an analogy to the human brain, hence the name neural networks, because we have networks of neurons in our brain. Now, a simple network, neural network shown on the left, you have inputs shown in red, you have outputs shown in blue, and you have these hidden layers here shown in orange. I guess I'll call it orange. And you get little equations, little regression, piecewise equations between your inputs and your outputs. Deep learning neural networks, which are getting a lot of the press lately, simply have more layers, more hidden layers, a whole bunch of hidden layers between your inputs in red and your outputs in blue. So those hidden layers, think of them as piecewise regression coefficients, very closely related to correlations, right? So there's a book called The Book of Why, written by Judea Pearl. I'll talk more about him momentarily. He won the Turing Award. That's the man I was thinking about, Turing. The Turing Award, and I'll show a picture of that. And he wrote a book called Causality and a book called The Book of Why. And in both of them, he references this ladder of causality and talks about the layers of artificial intelligence. The lowest layer being association, the middle layer being an intervention, the highest layer being counterfactuals. So the lowest layer showing an owl here and a robot. This middle layer showing a baby and a caveman. The higher layer, which you think, of course, must be more advanced, you see an image of Albert Einstein and space traffic and everything else, counterfactuals. So I'm reading from his book, The Book of Why. Machine learning programs, including those with deep neural networks, what I just talked about a moment ago, operate almost entirely in an associational mode at this lowest rung of this ladder of causation. They are driven by a stream of observations to which they attempt to fit a function, like a regression equation, in much the same way that a statistician tries to fit a line to a collection of points, as I've been discussing. Deep neural networks have added many more hidden layers to the complexity of the fitted function, but still, what drives the fitting process is raw data. This lack of flexibility, adaptability, and transparency, because those hidden layers are in fact hidden, is not in the least bit surprising. It is inevitable at any system that works at the first level of the ladder of causation. So let me go on for a moment. So moving from the world of correlation to the world of causation. And that involves another subfield of the world of artificial intelligence machine learning called Bayesian belief networks. So let me talk about Bayesian belief networks in a moment, but show a little bit. Here's a couple of books on Bayesian artificial intelligence and a book called Machine Learning, a Bayesian and Optimization Perspective. Now, it's interesting to me that the co-author of Bayesian Artificial Intelligence at the left has been promoted up Dr. Ann Nicholson. She's now the Dean of Monash University, a very prestigious university down under in Australia. But anyway, so Judea Pearl is the man who basically invented, if you will, Bayesian belief networks as a form of artificial intelligence. And he wrote the book Causality, shown on the left, that I'll talk about a little bit more, and the book of Why that I was just mentioning, with the subtitle, The New Science of Cause and Effect. Well, he gave an interesting lecture, and I'm excerpting just a couple of slides and modifying them a little bit from his talk. This is like 20 years ago. He gave a talk in Singapore, The Art and Science of Cause and Effect. Fascinating talk. It was an epilogue, it became an epilogue in his book, Causality, Models, Reasoning, and Inference. But I think most of us would be a little bit fascinated in the slide or two that I get from here. But let me go back to this idea here before I go into my linkage that I want to make. So again, from his books, Judea Pearl is saying, deep understanding means knowing not merely how things behaved yesterday, but also how things will behave under new or hypothetical circumstances in possible futures. Causality, causal models, are viewed as a litmus test distinguishing deliberate reasoning from reactive or instinctive responses. So, talking about birds and monkeys as animals, they can possibly be trained, reactive or instinctive response, fixing a broken wire, but that requires trial and error training. Deliberate reasoners, like us STEM people, us engineers, can anticipate the consequences of new manipulations before we even try those manipulations. So that's at the higher level, counterfactuals, imagining, retrospection, understanding, what if we do this? That's at the highest level. And that's what we're trying to go to. So he had another interesting comment that I thought you would appreciate on the next slide. So this is Judea Pearl slide that I thought the people in IEEE would really love. He took an image of a digital circuit diagram and he extols it. I love this. Let's start with an area that uses causation extensively and never had any trouble with it. Us engineers, engineering, yay us. Here is a circuit diagram, digital logic diagram, that shows cause and effect relations among the signals in a digital circuit. Its simplicity and familiarity are very deceiving. This diagram is one of the greatest marvels of science. Don't you feel proud of yourselves? I feel proud too. I did a diagram like this once, so I feel very proud. Great marvels of science. It is capable of conveying more information than millions of algebraic equations, probability functions, or logical expressions. What makes this circuit diagram so powerful is the ability to predict how the circuit will behave under abnormal situations. We can tell what would happen, what the output would be if we change this particular AND gate to an OR gate, for example. We could do what ifs. And notice the word predict. And our other title today, Predictive Engineering and Artificial Intelligence. So this is very much analysis of what we're trying to do in engineering, very analysis of what we're trying to do with predictive engineering, trying to predict possible futures. And that, according to Judea Pearl, is at the highest level of the ladder of causality, the highest level of artificial intelligence. So still staying with Judea Pearl, but also talking with another set of researchers in this field, in the field. So I'm pulling something from the Journal of Machine Learning Research from a few years ago. They talk about different ways of understanding causality rather than correlation. X correlates with Y, looking at causality. And they say basically causal relations can be determined in three ways. Domain knowledge provided by an expert. Secondly, performing interventions, basically controlled experiments. We'll talk about this relationship to predictive engineering momentarily. Using causal discovery algorithms, which I'll talk about a little bit later on, and this is from these sources over here. So in the world of predictive engineering, domain knowledge provided by an expert. In the world of predictive engineering, in the world of design for Six Sigma, we call that first principles modeling, basically theoretical equations, equations you can derive or equations you can get out of a textbook that somebody else derived. That's domain knowledge provided by an expert. That's in predictive engineering. Performing interventions, controlled experiments, that's what we use in statistics, use in predictive engineering. ANOVA for one factor, design of experiments for more than one factor, RSM for optimization when you have more than one factor. Those are controlled experiments in the world of predictive engineering, very much analogous to this way of getting a causal relationship in the world of artificial intelligence. And we'll get back to using causal discovery algorithms a little bit later on. And then Judea Pearl came up with a definition, an interesting kind of definition for a causal model. And in engineering, we use modeling a lot. Well, what's a causal model? He refers to it as an ordered triple of three sets of things, U, V, and E. U is a set of external exogenous variables whose values are determined by factors outside of the model. V are a set of internal endogenous variables whose values are determined by factors within the model. And E are a set of equations that show the relationships between the endogenous variables as a function of the variables in U and V. Well, in the world of predictive engineering, we call U, those exogenous external factors, factors outside the model, noise factors. We call V, the endogenous variables factored within the model, control factors. And those equations that relate them, we call transfer functions. Different terminology, but the same concept in predictive engineering. So hopefully making that tie in between causality in the world of artificial intelligence and predictive engineering that we talked about in our earlier two talks. And you see Judea-Pearl winning the Turing Award. Basically, they consider that the Nobel Prize of Artificial Intelligence about 14 years ago. So in the world of predictive engineering, one of the early things that we do in almost every predictive engineering DFSS kind of project is a P diagram. The P stands for parameter, where we have the noise factors, the exogenous variables, the control factors, the endogenous variables, and we have the functions, the E, the structural equations and things like that in a P diagram. So you see the analogy hopefully very clearly now. So causal relationships can be determined by those three ways. And let me just build on with, first off, domain knowledge, first principles modeling, theoretical equations, predictive engineering. So here's a diagram I think I've shown in my earlier guest talks, showing you what predictive engineering is. We need a model and we make it probabilistic. That model can come from theoretical equations. Those theoretical equations are basically domain knowledge provided by an expert, first principle model, theoretical equations. That's up here. ANOVA, design of experiments, performing interventions, controlled experiments. That's DOE, RSM, also ROE, ANOVA, regression and logistic regression. But when you have multiple factors, DOE, design of experiments, response service modeling, those are the same thing to give it to your model. So very much predictive engineering, very analogous to the way of coming up with this causal relationships in this causal artificial intelligence approach. So hopefully you got an idea now of what do predictive engineering and artificial intelligence have in common. Can predictive engineering help us better understand and leverage AI? So, give a few personal examples. Automatic reasoning, just as a little subset. So I actually got involved with AI when I was at Motorola. We were working in a semiconductor fab where operators would have to look under a microscope, as shown over here on the right, and they'd have to interrupt looking at the microscope to take notes on a sheet of paper. And then they'd have to focus through the microscope, then refocus and write notes on the sheet of paper. And we talked to the operators and they complained about this. It was very hard on them, very stressful, very hard to change their focus. It was hard on their eyes. It was hard on them in general. And so we brought in voice recognition, an early form of AI called VADIS, voice activated data entry system, where we basically trained it for each of the operators and let them be able to stay focused through the microscope, speak into a microphone, talk about what they're seeing, get the voice recognition and have it put out there on the system, recording the information for them so they did not have to keep on refocusing. And we were able to document it, published a paper about it back in 1980, what was about 35 years ago, resulted in a 23% improvement in productivity and 100% data accuracy. So we were rather proud of this and wrote a paper about it. Here's a more recent example of my involvement with AI, I guess trying to get a little bit of credibility with you folks a little bit. Came up with an idea a few years ago that we came up with as a patent. You see the list over there. Here's my name in there. Wearable defibrillation, shocking the heart, to apply a machine learning algorithm. Got a patent filed, started it in 2018, about 7 years ago. Finally got it filed a couple of years ago on that. And then most recently, I've gotten pretty much into Bayesian belief networks, a form of artificial intelligence. Here's one I built this past year, working with a company I'm working with to build a Bayesian belief network for supply chain that would be resilient against things like global pandemics, disasters, earthquakes, hurricanes, war impact, and things like that, and being able to model and optimize how the supply chain would be able to recover from these problems. And actually, building a tool called Agena.ai, Agena Artificial Intelligence, and I also can turn it into a web app, and so it actually kind of functions, but I'm going to improve that model in a little while. So we can basically understand it. We understand kind of the statistics behind it, the predictive engineering concept, and just leveraging AI. Lastly, and this is rather ambitious, could predictive engineering help us improve on some of the AI issues, artificial intelligence issues that we've spoken about? Well, again, going back to what do predictive engineering and artificial intelligence have in common? We have these statistical methods that we talked about: correlation, linear and logistic regression, also using probabilities. Okay, so I'm going to show you something. This is from an article. I'll show you the title of the article momentarily. This is an illustration of ChatGPT's approach according to the article. ChatGPT's approach is also called generative artificial intelligence, LLM, large language models. And according to the article that I'm about to show you momentarily, they believe it works by determining the probabilities of words and phrases following an earlier term. So I'm going to play with it, just have a little bit of fun. So I ask this generative IA, who is, who is or what is Eric Moss? So we type that in, it says Eric Moss, and then it has all these studies of probabilities, how often Eric Moss showed, followed by can be, is, was, knows, and understands, and here's the percent of the time. So we roll the dice. Eric Moss is, so that's the next word. Eric Moss is. Now we roll the dice. After Eric Moss is, what is the most likely thing? So we roll the dice. Smart, expert in Six Sigma, mean, knowledgeable, a nerd. We roll the dice. Eric Moss is a nerd. All right, let's try it again. What is ChatGPT? Incredible, amazing. We roll the dice. ChatGPT is bullshit. And that's the title of the article. Amazing. I just love the fact that somebody got a peer-reviewed article published with the title ChatGPT is bullshit, published just last year in Ethics and Information Technology. I love this article. I mean, just the title alone got me. ChatGPT is bullshit. All right, so I'm summarizing the article for you in the next few minutes. So what is ChatGPT? According to this article, large language models, LLMs, are becoming increasingly good at carrying on convincing conversations. The most prominent, the one that's gotten the most publicity, OpenAI's ChatGPT. So that's what they'll focus on in this article. But it also carries on for Google Bard's chatbot, Meta's Llama, whatever else. Besides being complicated bits of software, they're surprisingly human-like. Treating yourself, anyone can go to that OpenAI and ask a reading of text, and typically produces text that is almost indistinguishable, perhaps even indistinguishable from that of your average English speaker or writer. So Turing, after whom the Turing Society, the person I mentioned before, was a Turing Fellow, and June April won the Turing Award, which is like the Nobel Prize of Artificial Intelligence. Turing came up with a test for artificial intelligence. So during the Turing test, a human interrogator over here asked several questions to both a human responder and a computer, artificial intelligence, and determined which player is a computer and which is a human respondent. Here's ChatGPT. The conclusion: ChatGPT seems human. So according, interrogator. So according to the Turing test, ChatGPT actually is artificial intelligence to that definition. So fantastic. We have achieved what Turing was envisioning back in the 1940s. We've achieved it. It is wonderful. It is amazing. It is incredibly impressive. But things go wrong with it, and that's what they're talking about. However, large language models, LLMs, are doing considerably less than what we human brains or our human brains do. The most obvious difference between a large language model and the human mind involves the goals, the purposes of the system. We as humans have a variety of goals. Physical desires. We want food, we want sustenance, we want to find dates, whatever else. We have social goals, relationships. We have projects at work, projects at home. We create physical objects. Large language models don't have any of that. They simply aim to replicate human speech. Their primary goal is to produce human-like text. By estimating, as we've shown you, the likelihood that a particular word will appear next, given the text that came before it, as I tried to illustrate. So the machine does this by, as I just tried to describe to you, constructing a massive statistical model using a huge server farm, one which is based on large amounts of text, mostly taken from the internet. Given this process, it is not surprising that LLMs have a problem with the truth. The goal is not to be truthful. The goal is to provide a normal seeming response to a prompt, not to convey truth, not to convey information that is necessarily helpful. And they have some real examples. These are published articles. For instance, a lawyer recently prepared his brief using ChatGPT and discovered to his chagrin that most of the cited cases were not real. And there's a reference, Weiser 2023. And as a judge put it, ChatGPT produced a text that was filled with bogus judicial decisions, bogus quotes, bogus internal citations. Similarly, when computer science researchers tested ChatGPT's ability to assist in academic writing, they found that it was able to produce surprisingly comprehensive and sometimes even accurate text on biological subjects, given the right prompts. But when asked to produce evidence for its claims, it provided 5 references dating to the early 2000s, none of which actually existed, but all provided PubMed IDs, but of different unrelated papers. And this is from Cassie McFarland, 2023. So people call this AI, artificial intelligence hallucination. It seems to be hallucinating sources of facts that don't exist. And she's basically referred to that in both technical journals and popular contexts. And so they go on in this article, ChatGPT is bullshit, lies, hallucinations, and bullshit. And they actually define bullshit, according to a philosopher by the name of Frankfurt. So it's called Frankfurtian bullshit. So Frankfurtian bullshit and lying. Many popular discussions of ChatGPT call its false statements hallucinations, but they're not hallucinations. They're not lies. They are bullshit. ChatGPT is bullshit, the title of the article. So another class of misleading testimony from philosophers, bullshit, analyzed by Harry Frankfurt. Frankfurt understands bullshit to be characterized not by an intent to lie, an intent to deceive, but instead for a reckless disregard for the truth. So a student trying to sound knowledgeable without having done the reading, a political candidate, and we've gone through so many political candidates with our last election theory season, a political candidate saying things because they sound good to potential voters, a dilettante trying to spin an interesting story. None of these people are really trying to deceive, but they're also not trying to convey facts. The defining feature of bullshit, a lack of concern with truth, or an indifference to how things really are. So we have argued we should use the terminology of bullshit rather than hallucinations to describe what comes out of ChatGPT. As Edwards noted, the term hallucination anthropomorphizes the LLMs. They do not perceive, so they do not misperceive. They do not hallucinate. The case of a large language model like ChatGPT giving false utterances is not an unusual to deviant form. The same process occurs whether the output happens to be true. So that's why they call ChatGPT a bullshit machine. Like a human bullshitter, some of the outputs will be true, others not. Like a human bullshitter, we should be relying upon those outputs. So those are the problems. Possible approaches. So can mislead users. Reliance on correlation categorization can lead to artificial prejudice. Correlation can lead in terms of causality. I showed you 6 examples. AI based on big data can not work in situations where there's very little data, and LLM can generate bullshit. Some possible approaches, and I'll just show you really quickly in our last few minutes. Verify with sequential Monte Carlo, a methodology. Monte Carlo is a method we use in predictive engineering. Sequential Monte Carlo. I'll have a slide about that in an article you can read more detail. You can integrate with causal modeling. And there's some efforts going on at several universities. This is from Carnegie Mellon, working with University of Pittsburgh. I'll get there in a moment. Or lastly, integrate neural networks with Bayesian networks to form Bayesian neural networks. So let's start with the first one, verify with sequential Monte Carlo. So here's that article from MIT. Today's artificial intelligence systems routinely fail to distinguish between hallucination and reality, or bullshit and reality. If you follow that article, ChatGPT is bullshit. And here's the example similar to what Amit was mentioning a little was mentioning. So autonomous driving systems can fail to perceive pedestrians and emergency vehicles, sometimes with fatal consequences. Conversational AI systems confidently make up facts and often fail to give accurate estimates of their own uncertainty. So to try to deal with that, researchers from MIT and Cal Berkeley have developed sophisticated AI inference algorithms that generate collections of probable explanations of data and estimate the quality of those explanations. And it's based on a mathematical approach called sequential Monte Carlo, proposing probable explanations of data, tracking how likely those proposed explanations seem given more information. So that's one way of dealing with that challenge from MIT and Cal Berkeley. Another way working with Carnegie Mellon and University of Pittsburgh and a couple other universities as well, but those are the ones I'm more familiar with. Integrate with causal modeling. So causal modeling, also called causal learning. So some approaches. I'm going to illustrate the first one up here: non-normality residuals, de-separation, adjustment criteria, backdoor criteria, front door criteria, and Judea-Pearl that I mentioned earlier. His do calculus. Let me just show you non-normality. I took some real data, pulled it off the web, of blood pressure versus age, and I made a little plot of it and kind of highlighted on it the histogram and looked at the residuals. And you see the residuals when I make blood pressure as the outcome, and the residuals when I have age as the outcome. Does increased blood pressure cause you to age, or does you getting older cause your blood pressure to go up? And the one that's less normal, which is this case, is the direction of causality, non-normality residuals. And you see this looks less normal than this, and that's the case, it is less normal. So that's one way of understanding causality, is looking at the statistical data, looking at the residual. Other ways mentioned de-separation, adjustment. A lot of these are in some of Judea-Pearl's books and some other books as well. And they have collected a whole group of these methods on this Carnegie Mellon website, cmu.edu, called Tetrad. Software suite for graphical causal models. Can be used with a graphical user interface, or can be used with Python, PyTetrad, or R, or PyTetrad. 20 theoretically reliable, well-tested search algorithms for causal models. Free tool, you can download it for free, 35 years of algorithms developed by philosophers, computer scientists, and statisticians. And won a prestigious award, the SAIL Award, the Super Artificial Intelligence Leader Award. And I have a little screenshot of one of their screenshots of their screen from Tetrad. Also, lastly, you can integrate neural networks with Bayesian networks. They call that Bayesian neural networks, and I don't have enough time, but basically they have a tutorial for deep learning, how to convert, or how you can deal with a Bayesian combination with neural networks. Bayesian networks, neural networks combined into Bayesian neural networks. A little bit about why you should use Bayesian neural networks. Another one, an introduction and survey of Bayesian neural networks. So that's what I wanted to cover today. Let me go ahead and pause for a moment, and I'll see if I can answer some of the questions, but also see if there's more questions. Let me take a drink of water before I do.
Feel free to drop your questions in the chat. Either Eric or I could read them off.
Yeah. So no. Otherwise, autonomous vehicles would not have problems in snow and other rare cases. So yeah, I think they've kind of worked around and found ways to get around them. I'm not sure if they created a causal model to deal with that or create that as an exception. I think somebody just raised their hand, so I'll go in a moment. I'm not sure what Uma was talking about, interrogator. Probably I said the word wrong. Perplexity.ai provides reference for its responses. Excellent. Our slides posted elsewhere, somewhere. Yeah, I sent the PDF files, and I think it's going to be made available to you. I'll let you kind of respond to that. And somebody raised their hand. Who raised their hand? Okay. Well, anyway, the slides will be shared by Brianna. I think I'm not sure where she's going to post them or make them available to people.
If you registered for the event, or if you put your email in for when you join this meeting, I should have your email so I can send it out after this meeting.
Okay, so awesome. Yeah, thank you. Very good and rich lecture. Thank you. Yeah, we are video recording it, and it's going to be posted, but it takes a while. I think WebEx has to process it, and then we have to post it. What do you think will happen if generating AI starts generating on generated AI? I can't even speculate it. Okay, thank you. Yes, very good session. Thank you, Mahendra and Bassam. Of course, there's all sorts of ways that AI can go even further wrong, and I'm hoping we can get it on a path where it goes right for us. I guess there was a big investment the other day to bring more ability of AI, and investing a lot of money and having more AI. Now we're having a competition with other countries like China right now about trying to be the leaders in generative AI. So hallucination is I'm not sure if I call it a bug so much. It's kind of a nature of how we set up generative AI, or large language models, as I try to describe, and it's described a little bit more detail in the article, which we can give you a copy of the article if you'd like. Thank you, Thomas, and thank you, Deepak, and thank you, Mahendran. All right, folks, I think we're kind of out of time. Be excellent to each other and party hard, dudes. It's the weekend. Yay.
Great. Thanks, Eric, and thanks everyone for attending this session. As I mentioned, I will send out the slides to everyone who entered their email either via registration for this event or entering this meeting. I will also send out a recording link once it's available. We might put it on IEEE TV, but unsure yet. But regardless, we'll send out a link to all of the information. And I'll also send out Eric's email if anyone wants to contact him directly for follow-up questions. Sorry we didn't have a lot of time, but definitely appreciate everyone for attending. And thank you again, Eric, for an awesome and engaging presentation.
Thank you. Have a wonderful day. Have a wonderful weekend.